and good afternoon. In this 30 minutes, I want to talk about the atmospheric neutrino experiment. Well, I decided to organize this talk like this. Well, first I have an introduction, and actually that is the kind of story before October 2007. Then I want to talk about the recent progress, that is the last 10 years. Then I'll talk about the possible future atmospheric neutrino experiments. Well, okay, I guess everyone knows how atmospheric neutrinos are produced. Anyway, we use the atmospheric neutrinos to study neutrino oscillations in recent years. But, well, initially, more than 50 years ago, atmospheric neutrinos were discovered by two extremely deep underground experiments. One was carried out in South Africa, and another one in India. And both of them were located really extremely deep underground. For example, the South Africa experiment was located, I believe, more than 3 kilometers underground. Anyway, these experiments discovered atmospheric neutrinos, and, well, at least one of the two experiments, South Africa experiment, continued the observation of atmospheric neutrinos. And they published their data in 1978. This graph is from their paper. And, well, you can see the atmospheric neutrino, cosmic ray muon spectrum, component, and also the neutrino-induced muon component. And, well, of course, it's clear that they observed neutrino-induced muons. But if we carefully read the conclusion of this paper, they noticed that their data are fair agreement with the expectation, namely flux. Predicted over flux observed was 1.6 plus minus 0.4. Well, if we carefully read, that means there is a kind of deficit of the muon neutrinos in the data. Of course, they cannot claim deficit because there was about 30% uncertainty in the predicted flux. Anyway, there was some kind of hint already 40 years ago. And then, in the 80s, different type of experiment began. That was the proton decay experiments. Well, the proton decay experiments in that generation try to observe proton decays with the lifetime of about 10 to 30 years. That was predicted by the ground unified theories at that time. And of course, these experiments had to study atmospheric neutrinos as the most serious background for the proton decay searches. Then, some of these large underground proton decay detectors observed a deficit of atmospheric muon neutrinos. Here, I show you the summary of the muon event deficit. Well, the horizontal axis shows mu over E ratio of the data over the same ratio of the Monte Carlo prediction. And you can see in some of these experiments, a significant deficit of the muon neutrinos were observed. And with this definition, we can avoid the uncertainty in the total neutrino flux. So we thought that there might be some physics behind the deficit of these neutrinos. However, the detectors in the 80s and early 90s did not have powerful, was not powerful enough to find the reason for the deficit. Then, the next generation experiment was the super Kamiokande experiment. It is a much larger detector than the previous generation experiments. It is a 50 kiloton water Cherenkov detector. And this experiment observed really a significant number of atmospheric neutrino events. And actually, already in 2 years after the start of the experiment, Super Kamiokande collaboration was able to report the deficit, report the atmospheric neutrino study results. And, as you know, Super Kamiokande observed the deficit of upward-going muon neutrinos very clearly. And from this data, and together with some other supporting data, Super Kamiokande concluded that the observed zenith angle-dependent deficit and other supporting data gave evidence for neutrino oscillations. Well, okay, that was about 20 years ago, and now I want to move on to the recent 10 years. And of course, in the last 10 years, Kavli IPMU has been playing an important role in the studies of atmospheric neutrinos. And in fact, the main player in the last 10 years in the atmospheric neutrino studies is the Super Kamiokande experiment. And I just want to tell you that Super Kamiokande has been trying to improve the data statistics in the last 20 years. In the left, you can see the Super Kamiokande data that was presented at Neutrino Conference in 1998. And at that time, the number of events in this plot was only about 500. Now, if we make the same kind of plot with the most updated data, that is shown in the right, and you can see the total statistics is about 6,000 events. So the data statistics was improved by more than a factor of 10 compared with the, say, 20 years ago. So it is possible to do detailed studies of neutrino oscillations. And I'm going to talk about just 2 topics from the recent Super Kamiokande data. One is the tau neutrino appearance. The question was, if the oscillations are really between nu mu and nu tau, we should be able to observe nu tau appearance. Yes, in fact, yes. The half of the upgoing neutrinos should be nu tau if the mixing angle is maximal. Then, of course, we should observe charge current nu tau interactions. However, we expect that it may not be so easy to observe nu tau events because, in many cases, the final state of the tau neutrino interaction are only, say, many particles. In fact, according to the Monte Carlo of Super Kamiokande detector, the expected nu tau signal is like this. So you can see many Cherenkov rings, and this clearly tells us that it's not possible for Super Kamiokande to identify new tau events by an event-by-event basis. Therefore, in Super Kamiokande, we tried a statistical analysis knowing that new taus are upward going only because they are produced by, they are generated by neutrino oscillations. So, for some time, Super Kamiokande has been working hard to try to enhance the tau-like events and try to see the evidence for new tau appearance. And this one shown in the right shows the most updated data from Super Kamiokande for tau-like events. And of course, there are still significant backgrounds, but data clearly shows some excess above the non-new tau backgrounds. And that, in fact, the red part is the estimated new tau signal. And at present, the new tau appearance is confirmed at 4.6 sigma level, and that is also consistent with the OPERA experiment result. Okay, anyway, we are happy to observe the evidence for new tau appearance. And of course, there are various experiments that studied neutrino oscillations in the last 20 years. And in short, the present status can be summarized in this table. And I'm very glad to say that basic structure for three flavor oscillations have been understood. However, we know that we do not understand everything. For example, actually, we do not know if the mu3 mass state is the heaviest or the lightest. Or we do not know if CP is violated in the neutrino sector. Therefore, we are still working hard to understand the neutrino oscillations or neutrino properties. And from now on, I'm going to talk about the studies of neutrino mass hierarchy. Now, this view graph shows the oscillation probabilities for neutrinos and antineutrinos as a function of neutrino energy and the Zin's angle. And you can see there's a significant difference between neutrinos and the antineutrinos. The difference is due to the matter effect. And here we assume that the nu3 mass state is the heaviest. And if we assume that nu3 is the lightest mass state, then the oscillation probability shown for neutrinos should be seen in antineutrinos. So by using this effect, we should be able to tell the mass hierarchy of neutrinos. And in fact, as you can see, we would expect resonance effect around 5 GeV neutrinos. And this should be observed as an excess of upward-going neutrinos in the multi-GeV energy range. So we try to see if there is an excess effect in the electron neutrino events. And this is the data. And actually, very unfortunately, with this plot alone, we are unable to clearly say if there is a very large large effect expected due to new mutant new E oscillations. Anyway, using all kind of data observed in Super Kamiokande, we carried out a statistical analysis, and the result is shown in the right. And you can see that the data favors normal mass hierarchy, and the delta chi-square for the normal mass hierarchy and inverted mass hierarchy is about 4.3. That is 2 sigma effect. And we think, actually, data favors normal hierarchy, and this is quite interesting. But, still, this is 2 sigma effect. So I think we need more data. Therefore, we have to think about the future neutrino experiments. And of course, I hope that Kavli IPMU will continue to play an important role in the studies of atmospheric neutrinos. Now, because of the importance of the neutrino mass hierarchy, there are many experiments planned. And this is the list of the future experiments that will tell us the neutrino mass hierarchy. There are this many experiments, and actually, I'm rather happy to say that among these 7, 4 atmospheric neutrino experiments. And from now on, I'm going to talk about one of the experiments, that is the HyperK experiment. First of all, let me show you this slide. In the past, Kamiokande and Super Kamiokande water Cherenkov experiments contributed a lot to neutrino physics. Therefore, we think that HyperK is a natural extension of the previous experiments. And I want to tell you what we are thinking about the HyperK detector. It will be located in Kamioka, about 8 kilometers south of the present Super K detector. And the HyperK detector will be a cylindrical tank with the diameter of about 74 meters and the height of 60 meters. The total and the fiducial volumes are 0.26 and 0.19 megatons, respectively. So this is going to be really a big detector, and therefore we expect that we could improve the measurement of the neutrino mass hierarchy. And in fact, if we operate the HyperK detector for 10 years, the data could tell us the mass hierarchy at least at the 3 sigma level without relying on the neutrino beam. That means atmospheric neutrino only. And of course, if the data from accelerator beam are combined, the constraint to the mass hierarchy should be much stronger. That is for 10 years of HyperK. Then I have another topic, that is the tau neutrino appearance. As I said, this is the present status from Super Kamiokande. Now I want to talk about the tau appearance in HyperK. And here, I assume 5.6 megaton years of exposure. That is HyperK 30 years. Anyway, in this high statistics, the statistical significance is no more an issue. The normalization of the charge current neutral cross-section relative to the charge current nu cross-section can be constrained to 7% accuracy. And actually, this measurement will help understand the charge current neutral cross-section near the threshold, which is actually not known precisely. Now, I want to show you another example of studies of atmospheric neutrinos. That is the study of the chemical composition of the Earth's outer core. Well, please remember that the matter potential is proportional to the electron number density. Therefore, the matter resonance effect is depending on the chemical composition. Therefore, the detailed studies of atmospheric neutrinos could tell us the chemical composition of the Earth core. And actually here, we assume 10 megaton year of exposure, which is about 50 years of HyperK. But anyway, if we have a high enough exposure, then we could differentiate the, say, pure iron core and, say, extreme cases, red or water core. Anyway, well, we are somewhat sensitive to the chemical combustion of the Earth core. Now, in the remaining time, I want to talk about the HyperK-related issues. First of all, well, since the title of this talk is atmospheric neutrinos, therefore I only talked about the atmospheric neutrino physics with the future HyperK detector. But, well, HyperK is not just for atmospheric neutrinos. It can be used for the long baseline neutrino oscillation experiment. That is the main goal is the CP violation. And also, it can be the next generation proton decay experiment, solar neutrino experiment, supernova neutrinos, and so on. So the next generation experiment like this should be very important for the development of neutrino physics. Now, I want to talk about the status of HyperK briefly. First of all, the design report has been written in February last year. Then, Science Council of Japan evaluated HyperK as one of the high priority projects in the Master Plan 2017. After that, the Ministry of Japanese Ministry of Education, Culture, Sports, Science, and Technology, MEXT, evaluated high priority projects listed in the master plan in this summer, and HyperK was listed as one of the 7 projects in the MEXT roadmap. Therefore, HyperK must be a serious candidate for the next generation large science projects by MEXT. And because of this development, on October 1st this year, half a month ago, a new organization was formed based on members from ICRR, Kavli IPMU, and School of Science in the University of Tokyo to promote the HyperK project. And, well, certainly we are asking our funding agency to approve the HyperK project as soon as possible. Okay, let me summarize. Well, atmospheric neutrinos have been playing a very important role in the neutrino oscillation studies, and atmospheric neutrinos are likely to contribute more to neutrino oscillation studies. And future neutrino oscillation experiments can also contribute to the other physics, future atmospheric neutrino experiments, such as long baseline neutrino oscillation, proton decay, solar neutrino supernova. And finally, I want to repeat that HyperK is proposed as the next generation neutrino experiment. Okay, that's all. Thank you very much.